Good morning. I'm Gyugeun Yoon from Yoon University, and I'm so glad to be here. This nice city, nice university. So I'm also glad to present this subject to you all, the integration of recommender system in mobility services to improve seniors' accessibility. So I'd like to start with addressing challenges in senior mobility. So in 2009, almost 10% of all trips and all miles traveled are conducted by seniors. And in between 2001 and 2009, the number of senior transit users are increased by 55%. And we can assume that this trend will continue because we are living in aging society, not just for this United States, but also all over the world. So our team, the University of Texas El Paso and New York University, conducted a survey to understand seniors' mobility needs. And we collected about 500 responses from both cities, and we found that their top trip concerns are very similar to ours. Like they concerned about travel time and cost, weather, and the punctuality of system. Yeah, one remarkable point was they had very few experiences on paratransit and ride-sharing services, even though they own smartphone by 50%, around 50%. But there's a little discrepancy because the market expanded during last decades. So you can see the proportion of the increase was 24% in the mobility service in New York City, thanks to some app-based transportation services like Uber, Lyft, Via, Juno, and other stuffs. But you can see among the top 8 smartphone apps used by seniors, we cannot find any mobility solutions. That means that there are general lack of solutions related to mobility for seniors. And meanwhile, the mobility services also have been suffer from cost and schedule changes. For example, the access of ride, the paratransit services for seniors and the disabled in New York City, they served 144,000 users in 2015 and spent $461 million. In average, they spent $71 per trip. Yeah, that's very huge because the fare is in the level of about public transit fare. Also, they have experienced lots of no-shows and cancellations, which disturbs their predetermined operation plan. So we had a thought, what if the mobility on-demand service can recommend destinations for users? Initially, the vehicle serves the predetermined user's origin and destination, but when we can recommend the yellow square like that, if it is more attractive to user, then user can visit better place and system can operate system with lower cost. That means both can be winners. So there are three major benefits can be enjoyed. The first one is the mitigating the system cost, and second one is they can visit better place with higher utility, and especially for those who may not access the contemporary information about establishments, then they can reduce that exploration cost also. And finally, the system can learn the user's behavior, and they can elaborate their system to make their recommendation much more accurate. So we studied the destination recommender system of mode service. Before going further, we had to know how the destination recommendation work. But this is not the very new system because all famous online services like Amazon, Netflix, or Google are using this. They use information from prior selection or prior trials to recommend choices in a current trials or future one. So let's say there are J alternatives are provided to users, and the system collects the information what they chose, and under the using a certain algorithm, they can recommend the best one, which is very close to the optimum alternative to each user. For example, this is just an example of what I'm saying. So the algorithm one shows the poorer performance than algorithm 2 in terms of the average regret. The regret means the discrepancy between the optimal alternative and the recommended alternative in terms of utility. But problem is not that easy, because in destination recommender system, we also have to look into routing constraints, which is not related to the services like Amazon, because they don't care where the users are. But in our system, we also have to look into where the user is located and what's the existing route is operated and how long it will take. So even though we have the same alternative set, their feature, it changes time by time, trial by trial. So in the algorithm, we also had to look into that routing constraints and incorporate that into our objective. So we proposed an algorithm using an upper confidence bound, which is cited from the Lee et al. The upper confidence bound means that we can assure the upper bound of the cumulative regret. How it works is a new customer requests the recommender service, and this algorithm evaluate alternatives based on the destination preferences like ratings and the increase in routing cost. After that, the algorithm doesn't recommend the highest utility one, but it also considers the future optimization based on learning. This is the illustration of the embedded routing function. So initially, on 0 point, we assume that there is initial vehicle location, and we have to serve several passengers all over the network from the circle to the square. You cannot serve the passenger from the square to circle because the passengers are all located in the circle initially. So we consider all possible links between nodes, and we build a route which is shortest path. We don't solve this in full factorial, but we use the heuristics called insertion heuristics, which can achieve about 5% or 10% optimality gap. And during the operation, a new customer, the circle red, bumped in and request for a new service. Then we have to recall all possible alternatives and evaluate their ratings and consider all increasing routing cost. And when we recommend this point to the user, and after they accepted it, then we rebuild the route and serve all passengers. So this is the structure of the algorithm. So it consists of 4 major parts. The first one is build a route with existing passengers, and second part, we accept the new request, and and the third part, we evaluate the features of the alternatives and decide which one to recommend. There are 2 different recommend schemes there. The first one, during the learning part, which is the part we have to initialize the algorithm, we just randomly give the alternative to them and observe their responses to that, so we can stabilize the output of the algorithm. In the last part, in the latter part, the exploitation part, we recommend the alternative based on what I explained previously. In the last part, we observe the response and archive their responses and update the parameter of the algorithm. So we conducted 3 different simulation experiments. The first one is the verification. We gave the algorithm 100 destinations, and we assumed that users will behave and follow the binary logic model with the utility function of that. We have 2 variables. One is rating of each alternative, and the other one is the increasing routing cost. So during 1,000 simulated trials, we draw this diagram, which looks nice. You can see the slope of cumulative regret decreases as we repeat the trials, which means the algorithm succeeds recommending the best alternative to users as they learn and archive choice more. And also the parameter could be estimated very well. Like you can see the percentage error is around 5%, which makes sense. And the second experiment, we add some disturbances to the constant. In the universal constant, we don't think about the heterogeneity of users and alternatives. But when we move on from theta 0 to theta s, then now we can consider the difference of each alternative that we cannot capture in that utility function. And moreover, we could go on to theta ns, which also made some distribution for the constant themselves. And also, we considered 3 other recommendation criteria. The first one we gave just randomly without any decision. And second one, we just picked the alternative with the highest rating. And the third one, we picked the alternative with smallest routing cost increase. And fourth one, it was our algorithm. So we conducted 50 simulations for each case. And you can see the red figures are the results of our algorithm, which performed way better than other recommendation schemes. So finally, we applied this algorithm to real data. We browsed the real trip distribution in Manhattan of internal trips. And also we browsed some restaurant information from Yelp and to use them as a pool of our alternative. We didn't consider the real network, which consider the Manhattan distance. Instead, in this case, we just simplified the problem that the vehicle connects each points in Euclidean distance. Yeah, the objective was we generated different similar settings and to see how the settings like vehicle capacity or congestion level or the degree of exploration affect the performance of the algorithm, which is the acceptance rate, which is the proportion of the users who accept the recommendation. So this was the setting. You can see the structure of the utility function is exactly the same, except for the constant. We used the -5 previously, but now we added the disturbances to the real data, and in every simulation we randomized the parameters and ran the code. So after 200 simulations, we found that the passenger arrival rate, which represents the demand level, and the travel time per distance, which is the inverse of speed, and I can say it's the travel time move the same distance, unit distance, and we can interpret it in that way. The more passenger in the system and the faster vehicle speed we can operate, then there may be more acceptance to our recommendation. In conclusion, we suggest the mode with destination recommender system to help the seniors who wants to explore more in the neighbor, but who cannot access the information because some reasons, and not likely existing recommender system. We had to add some routing constraints, and we did it. And finally, we concluded that the demand level and actual vehicle trip speed affects the performance measure significantly. The UTAP plans to roll out the prototype to seniors, even though it does not include the physical operation, but at least they can find the responses from our seniors there. Also, we have to include some personal characteristics in the utility models. Now we just have some ratings and routing costs, but we also have to consider age, gender, or other existence of their symptoms. And also, finally, we try to seek other mobility solutions that is applicable with this algorithm. So before finishing the City Smart, the connected cities with smart transportation is another USDOT Tier 1 University Transportation Center, like here TRCLC, and Professor Joseph Chow was the PI of this project. Thank you for listening, and if there is a question, let me know. Thank you.